So, in today's lecture, we are going to look into different strain measures and then a little bit of polar decomposition theorem we will start. So, in today's lecture, we will cover this topic and partially polar decomposition theorem. In next lecture, we will cover the whole or partial polar decomposition theorem and volume change and area change. Okay. Now, coming to strain. Okay. So, to define strain, let us first again look into this picture. Okay. So, at time t equal to 0, our body occupies the initial configuration with volume B 0 bounded by surface del B 0. Okay. And then let P be a point whose material vector is x. Okay. And let us consider two more points q1 and q2 and their relative position vector with respect to P is dx1 and dx2 respectively. Okay. So, once forces are applied, the body undergoes deformation and then, so this is the deformation mapping. The body at time t, that is in the current configuration, has occupied this position where the volume is P and the surface is del B. Okay. So, the current position of point P is this small p, the current position vector of point P is small x and the current relative position vectors of point q1 and q2 with respect to point P is given by dx1 and dx2. Okay. So, this is a general setup that we have, and now what we do is we consider the scalar product, okay, of this elemental material vectors dx1 and dx2, okay, as they deform to spatial vectors dx1 and dx2 respectively. Okay. So, what would happen as the material vectors deform, they will undergo what is called stretching, which means there will be change in length, okay, of the vectors. So, PQ1, PQ2, these two vectors will stretch, okay. They may elongate, they may compress, but there may be change in length, okay. And also the angle, okay, this angle between the two vectors, say theta 0, let us say theta 0, this angle between the two vectors PQ1 and PQ2 will also change. Okay. So, as shown here, theta 0 changes to theta. Okay. Now, we can recall that the deformation gradient tensor, which is F, maps the material vectors dx1 and dx2 to spatial vectors small dx1 and small dx2. Okay. So, mathematically you can write the spatial vector dx1 is F times material vector dx1. Similarly, the spatial vector dx2 will be deformation gradient tensor F times material vector dx2. Okay. So, now we consider the scalar product of the spatial vectors dx1 and dx2, okay, which is shown here dx1 dot dx2. Okay. Now, we want to see how this scalar product changes and can we express this scalar product in terms of the deformation gradient tensor and the material vectors. Okay. So, now dx1 dot dx2, okay, because both are vectors. So, A dot B can also be written as A transpose B. So, we can write dx1 dot dx2 as dx1 transpose dx2. Okay. Now, using equation 20 and 21. So, from equation 20 I can substitute for dx1 which is f dx1, and then from 21 I can substitute dx2 which is f dx2. Okay. So, now I have f dx1 transpose f dx2. So, I can open up the brackets and I can write dx1 transpose f dx2. Okay. Now, this dx1 is a vector and then f transpose f dx2 again is a vector, okay, because f transpose f will be another second order tensor. So, it operates on vector dx2 to give you another vector. So, I can write, if I consider this as vector A and this is vector B. So, this is like A transpose B. So, I can write this as A dot B. Okay. So, I can write this expression as dx1 dot f transpose f dx2. Okay. Now, I can define a tensor C. Okay. I can define another tensor C, okay, as f transpose f, and this tensor C is called Wright-Cauchy-Green deformation tensor. Okay. It is a very important measure of deformation, okay, and this is called the Wright-Cauchy-Green deformation tensor. Okay. And this tensor is totally a material vector. Okay. Sorry, it is a material tensor. Okay. It is a material tensor because it totally resides in the material configuration or the initial configuration. Okay. I can, so this is the direct notation. Okay. This equation is the direct notation. I can express the same in indicial notation. Okay. So, this is the indicial representation of the equation, direct notation for Wright-Cauchy-Green deformation tensor. Okay. So, we have C capital Ij. Okay. So, that is the convention we follow, that indices pertaining to initial configuration are written in uppercase and indices pertaining to spatial configuration or the current configuration are written in lowercase. Okay. So, f transpose is nothing but f I comma I, okay, and then f is f I comma j. So, you can see I is common, but the I in the first f is on the left hand side and I in the second also is on the left hand side. So, I can write this as f I transpose f I j, okay, which will make I in the first f go to the right hand side, and therefore, this notation over here is same as this expression over here in the direct notation. Okay. So, this is the indicial representation of the direct notation which is given by equation 24. Okay. So, Wright-Cauchy-Green tensor is a material tensor. You see both the indices are in capital, which means it resides totally in the material configuration or the initial configuration. Okay. So, if you substitute C is f transpose f in equation number 23, what you will get? dx1 dot dx2, that the scalar product of the spatial vectors is equal to material vector dx1 dot C material vector dx2. Okay. So, alternatively I can go the other way around. Okay. I can consider the scalar product of the material vectors dx1 and dx2. Okay. So, I can write dx1 dot dx2, and because both are vector, I can write dx1 transpose dx2. Okay. Now, I can invert the relation, okay, for dx equal to f dx. Okay. So, I can write the material vector in terms of the deformation gradient times inverse of deformation gradient times the spatial vector, okay, which is given here. Okay. So, this you can derive using this relation. You can take the inverse of this will be this f inverse dx1. Similarly, dx2 will be f inverse dx2. Okay. So, I can substitute for the material vectors in terms of spatial vectors, and I can get dx1 transpose f inverse transpose f inverse dx2. Okay. So, we have used equation 20 and 21, and therefore, we get the dot product of the or the scalar product of the material vectors as dx1 dot f transpose inverse dx2. Okay. Now, I can define another tensor B, okay, the symbol B as f transpose, and this tensor B is called the left Cauchy-Green deformation tensor. Okay. So, capital C was called the right Cauchy-Green deformation tensor, and B is called the left Cauchy-Green deformation tensor, and this tensor is totally a spatial tensor. Okay. So, in indicial notation, I can write B I j, okay, and both the indices are in lower case, which means B resides in the current configuration. B I j is f I I f j I. Okay. So, now, if I substitute equation 30 in equation number 29, I can write the scalar product of the material vectors dx and dx1 and dx2 as dx1 dot B inverse dx2. Okay. So, now I can express the scalar product of the spatial vectors in terms of the material vectors, or I can express the scalar product of the material vectors in terms of the spatial vectors involving f. Using f, I can do that. Okay. Now, let us consider what happens to the change in the scalar product of spatial and material vectors. Till now, we have computed the scalar product of the spatial vectors and the material vectors separately. Now, let us consider what happens to the change. Okay. So, what we will do? We will take the difference of the scalar product of the spatial vectors and the material vectors. Okay. And we have put 1 by 2. Okay. So, the reason for this will be clear when we go to constitutive relations. Okay. But right now, just consider that there is a factor 1 by 2 which is multiplied on both the sides. Okay. So, it does not change anything, we just have made an factor 1 by 2. Okay. There is a reason for this, we will come to it later. So, dx1 dot dx2 was, so first term was dx1 dot c dx2 minus dx1 dot dx2. Okay. Now, I can take dx1 out of the bracket from the left hand side, okay, that is what happens, and I can take out dx2 outside the bracket from the right hand side. Okay. So, this is what is there. So, what is left in the bracket? 1 by 2 c minus I. Okay. So, 1 by 2 c minus I is what remains. Okay. and then we write 1 by 2 C minus I as another tensor E, capital E. Okay. So, this capital E is a material tensor. It is called the Green-Lagrange strain tensor. Okay. So, capital E is called the Green-Lagrange strain tensor, and it is given by this relation E equal to 1 by 2 C minus I. Okay. So, in indicial notation I can write E I j is 1 by 2 C I j minus delta I j. So, delta I j is the chronicle delta in the material configuration. Okay. Now, I can go in the other way. So, in the previous slide we have substituted the spatial vectors in terms of material vectors. I can do the other way around. I can go and substitute the material vectors in terms of spatial vectors. So, dx1 is f inverse dx1 and dx2 is f inverse dx2. This I can substitute here, okay. And then what I can get is, after a little simplification, what I can get is 1 by 2 dx1 dot dx2 minus dx1 dot p inverse dx2. Okay. So, I can take dx1 out of the bracket from the left hand side, and I can take dx2 out of the bracket from the right hand side. So, this is what we get, dx1 dot 1 by 2 I minus b inverse into dx2. Okay. So, next we denote 1 by 2 I minus b inverse as another tensor E. Okay. So, lowercase e. So, remember Green-Lagrange strain tensor was a uppercase e, because it was a material tensor, and our convention is all the material tensors will be written in uppercase, okay, and all the tensors in the spatial configuration will be written in lowercase. So, we have written E, small e here. So, the change in the scalar product of the spatial and material vectors is now expressed as dx1 dot E dx2, okay, that is equation 35. So, here E is a spatial tensor, okay. Spatial tensor means it resides in the current configuration, and it is called the Euler-Allemans strain tensor, okay. It is called the Euler-Allemans strain tensor, and it is given by E equal to 1 by 2 I minus B inverse. Okay. In indicial notation, the same expression can be written as E I j equal to B 1 by 2 delta I j minus B I j inverse. Okay. Here delta I j is the chronicle delta in the spatial configuration. Okay. Now, let us consider a special case where dx1 is same as dx2, okay, is equal to dx. Okay. So, in the figure you see we have considered a material vector dx, okay, going from P to Q, okay, and let this material vector be written as dl, which is nothing but the length of the material vector times n. What is n? N is the a unit vector along the material vector p q. Okay. So, n is the unit vector along p q. So, as you know, a vector is nothing but its magnitude times the unit vector in that particular direction. Okay. So, I can write the material vector dx as dl into n. Okay. N is a unit vector in that direction. Similarly, in the current configuration, okay, the material vector PQ has deformed and has become spatial vector PQ. Let the length be dl. Okay. In that case, the spatial vector dx is written as the length of the vector times the unit vector along PQ. Okay. So, I can write the spatial vector dx as the length of the vector times the unit vector n. Okay. So, once we have this, okay, and because I said we can consider dx1 equal to dx2 as a special case equal to dx. So, what happens to the scalar product of the material and spatial vectors? So, dx1 dot dx2 becomes dx dot dx, okay, and then dx dot dx becomes dl square n dot n, okay. And because n is a unit vector, n dot n is equal to 1. So, what we get dx dot dx is nothing but dl square. Similarly, this dot product of the spatial vectors dx dot dx is becomes d small l square. Okay. Now, we can define a quantity called stretch. Okay. So, at this point I will introduce this stretch, okay, and we will use the symbol alpha. Okay. So, stretch is defined as the final length divided by initial length, okay, or final length I can also call current length. Okay. So, current length divided by initial length. Okay. So, that is the definition of stretch. Okay. So, whenever I use the word stretch, you can remember that it is the ratio of current length to initial length. Okay. So, now the change, okay, in square length of the vectors is what we consider. Okay. As the body deforms, what happens to the change in the square length. Okay. So, we have to compute dl square minus d capital L square, and this 1 by 2 is retained. So, this is nothing but 1 by 2. So, dl square is nothing but dx dot dx, and d capital L square is nothing but dx dot dx, okay, because dx is f dx now. So, I can substitute material vector dx as in terms of f dx here, okay, I can substitute it here, and I can get dx dot 1 by 2 f transpose f minus I into dx, okay. And I can recognize this term over here, f transpose f is nothing but right Cauchy-Green tensor C, okay. So, now I have dx dot 1 by 2 C minus I dx, okay, and 1 by 2 C minus I had defined in the previous slides as the Green Lagrange strain tensor E, okay. So, our expression 1 by 2 dl square minus d capital L square reduces to dx dot E dx, okay. Now, if I divide both sides, okay, if I divide both sides by capital dl square, okay, capital dl square, if I divide on both the sides, what I get dl square minus d capital L square divided by 2 dl square is dx by dl dot E dx by dl. And what is dx by dl? Okay. So, dx is the vector, dl is the length. So, vector divided by its length gives you the unit vector along the direction of the vector n. So, we get n dot E n. Okay. So, now if you remember in one of the previous examples when we were linearizing different strain measures, the third example was Green Lagrange strain, okay, 1D version of Green Lagrange strain. So, now we can derive that here. So, if I take n as E1, okay, if I take n as E1. So, n is a unit vector along the x1 direction E1, okay. So, which in vector notation is 1 0 0, okay, it is in the x1 direction. And if I substitute it here, okay, what do I get? I get only I will get E11, okay, you can do it yourself, okay, because E is a second order tensor, and if I write that in matrix form, it will be E11 E12, E13, E22, E21 sorry, E22, E23, E31, E32, E33. Okay. So, n is 100 and E is this quantity over here. So, if I take the dot, if I substitute everything here, I will get the resultant E11, and that was the expression for Green-Lagrange strain in one dimension. Okay. So, if you remember, this was the expression that we used. Okay. So, you can take different n's and you can get the physical meaning of the different terms of the Green-Lagrange strain tensor. Okay. So, like if you take n as E2, you will get dl square by d capital L square by 2 dl square as E22. So, what it means is like E11 equal to this expression means is E11 shows originally if you had a material element, okay, vector lying along the x1 direction, okay, whose length was d capital L, and now after deformation it becomes d small l, but along the same direction. Okay. Then the change in the square length divided by the original length square will be nothing but the first component of the Green-Lagrange strain tensor, which is nothing but E11. Okay. So, E22 will be, you take a material vector along the 2 direction and after deformation it becomes some other vector. So, the change in square length of the vector after deformation to before deformation divided by twice of the square of the length in the initial configuration is nothing but will be E22. Okay. Like this you can get the physical meaning of the diagonal components of E. Okay. We will come to off diagonal term later. Similarly, instead of in the previous expression where we started, we substituted the material vector, spatial vector in terms of material vector. I can go the other way around. I can replace the material vector in terms of spatial vector and I can derive the relation of change in square length of the vector divided by twice of dl square. Okay. So, dl is the current length as nothing but n dot E n. Okay. So, E is the Euler-Almansi strain tensor and n is nothing but the unit vector in the spatial configuration along the vector direction. Okay. So, in terms of push forward operation, okay, now I can do the push forward and pull back operations. Okay. So, in terms of push forward operation, okay, the material and spatial tensors can be related. How we can do that? So, you notice that 1 by 2 dl square minus d capital L square is nothing but dx dot E dx. Okay. This is derived just here. Okay. And 1 by 2 dl square minus d capital L square can also be written as dx dot E dx. Okay. So, the change in square length either you can express in terms of spatial quantities or you can express in terms of material quantities. And because the left hand side of both the equations are same, that means the right hand side of both the quantities should be same. Okay. That means I can write dx1 dot dx2. Okay. Now, for a special case, okay, I will just consider two different vectors instead of same vector dx1 dx2, okay, equal to dx, I will consider two vectors. So, instead of dx I will write dx1. So, dx1 dot E dx2 will be same as dx1 dot E dx2. Okay. And now, dx1 is nothing but f inverse dx1 and dx2 is nothing but f inverse dx2. Okay. So, I can write this expression as dx1 dot f inverse transpose E F inverse dx2. Okay. So, going from this step to this step requires one additional step that I request you work it out yourself. Okay. Noting that in the middle expression, the term on the left hand side of the dot is basically a vector. So, and on the right hand side also you have a vector. So, A dot B is A transpose B, and you can just simply play between the vectors and you can derive this particular relation. Okay. So, we see that the left hand side we have dx1 dot E dx2 and the right hand side we have dx1 dot F inverse transpose E F inverse dx2. Okay. So, both sides are same. So, I can interpret Euler-Almansi strain tensor as a push forward of the Green-Lagrange strain tensor. Okay. Remember, phi star and square bracket E meant it is the push forward operation of E. Okay. Now, pushing forward E or the Green-Lagrange strain tensor gives you the Euler-Almansi strain tensor, and the way this push forward is actually done is given by F inverse transpose E F inverse. Okay. So, this notation in the direct notation, okay, can be written in initial notation using following expression. Okay. So, E I j is nothing but F I I inverse E I j F j j inverse. Okay. So, that is the initial representation of the direct notation given here. Okay. So, that is the push forward operation. So, the push forward of the Green-Lagrange strain tensor gives you the Euler-Almansi strain tensor. Similarly, you can do the pullback operation. Okay. Instead of dx1 dot dx2, okay, I can start the other way around, okay, or I can just start from equation number 49. Okay. I can start from this expression and I can find Green-Lagrange strain tensor in terms of Euler-Almansi strain tensor using following expression. Okay. So, this is phi star inverse E. This means the pullback of the Euler-Almansi strain tensor will give you the Green-Lagrange strain tensor, and the way this operation is carried out is F transpose E F. Okay. So, if you have Euler-Almansi strain tensor and you want to pull it back to the initial configuration where you will get the Green-Lagrange strain tensor. So, what you have to do? You have to pre-multiply Euler-Almansi strain tensor by F transpose and post multiply it by F. Okay. So, F is present. Okay. Now, we come to the next topic. Okay. So, the physical meaning of all these strain measures we will actually see in the next class, where we will do some examples. Okay. So, the polar decomposition theorem. So, polar decomposition theorem, before we start, you remember that the deformation gradient tensor maps the material vector to the spatial vector dx. Okay. So, you had a material vector, okay, and then F operated on that material vector to give you the spatial vector dx. Okay. Now, when we were discussing tensors, we discussed that any tensor can be broken into a orthogonal tensor and a symmetric tensor. Okay. That is what called the polar decomposition theorem. So, in our case, the deformation gradient tensor F can be decomposed into an orthogonal tensor and a symmetric tensor as F equal to R into U, and this is called the right polar decomposition, because U, which is the symmetric tensor, lies on the right hand side of the orthogonal tensor R. That is why it is called the right polar decomposition. Okay. So, R is the orthogonal tensor and U is the symmetric tensor, and it is also called the material right stretch tensor. So, why the word stretch is here? Stretch we have already defined, okay, is the current length divided by original length. So, there is certain relation between stretch and U. So, we will come to it later. That is why it is called the material right stretch tensor. Okay. So, we can derive a relation between the right Cauchy-Green tensor and the material right stretch tensor U. Okay. Remember that F is C is F transpose F. Now, F from equation 51 is R U. So, if I substitute F as R U, I get R U transpose R U. Okay. Now, R U transpose is U transpose R transpose R U. Okay. Now, R transpose R is a orthogonal tensor. Therefore, R transpose R is nothing but identity. Okay. R transpose R is identity. Therefore, we have U transpose R U becomes U transpose U, and U transpose is same as U, because U is a symmetric tensor. Therefore, U transpose is U. So, you have U dot U into U, which is nothing but U square. So, the relation that we get is U square is equal to C, or the square of the material right stretch tensor is equal to the right Cauchy-Green deformation tensor C. Okay. That is how we can relate. Now, we can alternatively do what is called the left polar decomposition. Here, F can be decomposed as a product of a symmetric tensor V times an orthogonal tensor R, and this is called the left polar decomposition, because V, the symmetric tensor, lies on the left hand side of R. Okay. And V is also called the spatial left stretch tensor. Okay. So, the components of both the material right stretch tensor and the spatial left stretch tensor have some physical meaning. Okay. So, we will come to it, but right now just consider that the word, it has the word stretch into it. Okay. As we had done in the previous slide, we can find a relation between the left Cauchy-Green tensor P and the left stretch tensor V. Okay. So, we know that B is F transpose, and F from equation 53 is VR. So, if you substitute F as VR here, we get VR into VR transpose. Okay. So, VR transpose is nothing but R transpose, V transpose, and we have VR, and RR transpose is identity, because R is a orthogonal tensor. Okay. So, we get V transpose, and V is a symmetric tensor. Therefore, V transpose is V, and therefore, we can write V square. Therefore, finally, we derive B is equal to V square. Okay. So, the left Cauchy-Green tensor is square of the spatial stretch tensor V, left stretch tensor V. Okay. Now, the question comes, when you are doing a finite element computation, you need to carry out this polar decomposition of the deformation gradient tensor. Okay. So, you need to determine what is U, because U contains stretch. Okay. So, how do we do this polar decomposition? Okay. So, first we will look into how we carry out the right polar decomposition. Okay. So, the first step is, let us say we solve the eigenvalue problem, okay, where we find the eigenvalues and eigenvectors of the right Cauchy-Green tensor C. Okay. So, let lambda 1 square, lambda 2 square, lambda 3 square be the 3 eigenvalues of C. Okay. Remember, we have not written lambda 1, lambda 2, lambda 3, but rather we are writing lambda 1 square, lambda 2 square and lambda 3 square. There is a square which is present, and let n1, n2, n3 be the eigenvectors of C. Okay. So, in the first step, we find the eigenvectors of C. So, that is done by writing C in matrix notation. Okay. So, C is C11, C12, C13, C21, C22, C23, C31, C32, C33. Okay. So, once you have this 3 by 3 matrix, you can solve for the eigenvalues, eigenvectors of this matrix, okay, which is nothing but the right Cauchy Green tensor. Okay. So, once you have found out the eigenvalues and eigenvectors using spectral decomposition theorem, I can express C as the linear combination of the eigenvalues times the tensor product of the eigenvectors, which is summation over alpha, alpha goes from 1 to 3, lambda alpha square, n alpha tensor product n alpha. Okay. This is nothing but lambda 1 square n 1 tensor product n 1 plus lambda 2 square n 2 tensor product n 2 plus lambda 3 square tensor product n 3 tensor product n 3. Okay. So, now I have determined the eigenvalues, eigenvectors. Now, I know the relation u square is C. So, u will be nothing but square root of C. So, from your linear algebra, you would recall that to find the square root of a matrix, what we have to do? We have to find the eigenvalues and eigenvectors, and then we take the square root of the eigenvectors and use the spectral decomposition, because eigenvectors do not change. So, eigenvalues we take the square root and use the spectral decomposition to reconstruct the square root of the matrix. So, here we have to take the square root of C, which means I take the square root of the eigenvalue. So, eigenvalue of C was lambda square. So, it becomes lambda. Okay. So, I have lambda and then the eigenvectors remain same. So, I have n alpha tensor product n alpha. So, u will be nothing but lambda alpha n alpha tensor product n alpha, okay, summation over 1 to 3. Okay. So, this will give you, step 3 will give you the right stretch tensor u. Okay. So, once you have u, okay, and you already have f, f is given to you, that is why you are doing the polar decomposition. Okay. So, from f what we do? We first calculate C. Okay. So, C is f transpose f. Okay. So, here I should have written one more step, say step 0, we can write, imagine C as f transpose f. Okay. Now, f is already there with you, you have in step 3 you have computed u. Now, the orthogonal tensor R will be nothing but R equal to f u inverse. Okay. So, you take the inverse of u and then you pre-multiply u inverse with f to get R. Okay. So, R can then be obtained. Okay. Why we need to do this kind of polar decomposition will be clear later. Okay.